Okay, so this is lecture 6, and today is the 15th of January. All right, so let me first briefly summarize again what we have done over the past two sessions. We have mainly focused on the concept of moments. So we introduced the concept of moment, of a force, about a point, and about an axis, okay, both in 3D and 2D. In 3D, as we said, if you have a force in space and you want to find the moment of that force about an arbitrary point O, you just simply connect that point to anywhere along the direction of that force. Obviously, anywhere means to a point for which you have the coordinates, right? And typically, as you've seen from example problems, a force is given acting along some direction, and 2 points along that direction are given. So connect O to one of those two, and then simply by setting up this determinant, which consists of first row is ijk, second row are the x, y, z components of this vector, which is position vector, and the third row are components of this force. The outcome of this determinant would be something like this, which is the vector equation for this moment, okay? And if you want to find the magnitude, if you've been asked to find the magnitude, you just simply take the square root of the sum of the squares of the components. So that's in 3D. Now, if you have a 2D problem, that is the force and the point about which you want to find its moment are on the same plane, this becomes a whole lot easier because as far as the direction that this force rotates the object about point O, it's going to be either this direction clockwise or counterclockwise. Because if you draw a position vector here, the cross product of this and this force is always perpendicular to this plane, but depending what direction this force is, that rotation takes place about this axis, either in the positive direction or in the negative direction, which we forget about that in 2D. We say, since it's always along this direction, that is a moment in 2D always has a vector equation, which would be this, okay? All we care about is the sign of this. And the sign of that can be determined this way. If you have this point, you just simply draw a line perpendicular to the direction of the force. So you find the vertical distance, magnitude of this moment would be the magnitude of the force times that distance. Direction would be found by imagining that you have this is a linkage. So if the force moves this way, this linkage is going to rotate in this direction, which is clockwise, right? We consider that negative. If the force was like this, and you had this point like this, right? So if the force moves this way, this linkage moves that way. So that is considered positive. The third topic we covered was moment about an axis, or actually, I should have, um, this was actually 1 A, and this was 1B. So this is the second topic about an axis, which is this. If you have a force and there is an axis here, D, you want to find the moment of this force about this axis. Again, this axis is given by a couple of points, by the coordinates of some point is defined. So the first thing is you find the moment of that force about a point along that axis. That means you draw, again, a position vector, like in this case. So this moment obviously would be found that same way. I, J, K, R, X, R, Y, R, Z, and F, X, F, Y, F, Z. Once you found this, then you consider the unit vector along that direction. So set up the equation for the unit vector along that direction, and the moment of this force about that axis D would be dot product of this moment and the unit vector along D, which would be a number, would be an algebraic value, because the outcome of a dot product is always a number. Any questions? If not, we're going to continue. You remember I promised you that the first 2, 3 weeks of the course will be focused on forces, their summation, resultant, 2D, 3D, equilibrium of a particle, rotational action of a force. So we are going to bring that sort of hopefully to a closure by next week. So the last topic dealing with forces that we are going to introduce is what we call a system of coupled forces, which is a special type of moment. That's what we are going to introduce. So what is we call that a couple system. So what is a couple system? If you happen to have two forces that are equal in magnitude, parallel to each other, opposite in direction, we call them a couple system of forces. A couple system of forces. You've dealt with this situation, I'm sure, before. Think of the wrench that you use to change your tire. You apply your hand, one hand in this direction, another hand in this direction to tighten, or the opposite way to loosen the bolts, right? So you are exerting two forces equal in magnitude, opposite in direction. There are many other uh, situations deal with a coupled system. Opening a jar. When you're opening a jar, right? When you put your hand here trying to open it, you're basically putting a force here, putting a force here that rotates this, and these two are equal. But anyway, so we want to see what is the significance of these two. Well, intuitively, first of all, we can immediately see that no matter what the coordinate system is, sum of these forces is always zero. So what is the function of a coupled system? This is how we are going to observe that. So if the sum is zero, how about the moment that these two forces generate about an arbitrary point? Let's find out. If you have two forces like this, what happens or what kind of moment they generate about a point? Their summation is zero. In other words, they cannot move the object in a translational direction, in the direction that these forces are applied, because that action is zero along any direction. So look at the rotational effect. So we want to find the moment that these two forces generate about point O. In other words, what is the total moment that these two forces generate about O? Let me call moment one being the moment that this force, let me call this F1 and F2, knowing that, of course, F1 and F2 have the same magnitude. So moment one, which is for F1, is what? Would be R1 cross F1, right? Or R1 cross F, right? M2, which is for F2, would be R2 cross this F is in the opposite direction of that, so it's a negative direction of the other force. So this is the moment of the first one, this is the moment of the other one. So what is the total moment then that is generated? The total moment would be what? Would be R1 cross F, then minus R2 cross F. This is a vector summation, so you can simply write this as R1 minus R2 cross F. What is R1 minus R2? R1 minus R2 is this vector. What that means is this. In order to find the moment that these two forces generate about point O, all you need to do, consider a position vector from a point along this force to a point along that force, this position vector, and the problem then comes down to what? That means the moment of these two forces about an arbitrary point has nothing to do with the location of this point, is independent of this point. That is, the moment that these two forces generate is independent of location of the point. It only depends on the magnitude of these forces and the vertical distance between them, because taking the moment of this force, what R1 minus R2 cross F means is that you're taking the moment of this about this point. So this is a 2D problem. That is, okay, this is R1 minus R2, right? So what is the moment of this force about this point? Magnitude would be simply this vertical distance. That is this D. So it would be D times F. And what is the direction that that moment is? That is a 2D, so you can easily see that in this case would be in the uh, clockwise direction. So what this observation or analysis tells us is one, sum of a couple system is always zero. Conclusion number two is a couple system, okay, only represents a moment. Although these two look like two forces, they don't have the function of a force. They cancel each other. All they do, they can only rotate the object. And the magnitude of the rotation is that force times the vertical distance between them. And the direction obviously can be easily found either clockwise or counterclockwise. Since this moment is independent of any location, that means regardless of where these two forces or the couple system is acting on an object, it generates the same moment because the magnitude of that moment has nothing to do about where these two forces are applied. It has everything to do with the distance between the two and their magnitude. For that reason, we call this a free moment that is independent, is free of the location that these forces are applied. Okay? Any questions?
Yeah.
You please? Sorry, you can go ahead.
Okay. For the finding the rotation, is it always the force that's pointed in the positive direction, or like how do
No,
you
no, no,
determine
no.
the tip and tail?
Remember the way what I recommended. If this is the force, this is another force, right? This is the linkage, or this is the vertical distance, right? So if this is the linkage or this is the linkage, if this moves this way, this moves that way, what direction this is going to rotate? Has to rotate this way, right? So if this force was this and this force like that, think of this connection. If these two move this way, what direction this is going to rotate? This way, right? So that's how you find the direction. Does it explain?
Yeah, it depends on
Oh,
both forces. Thanks.
sure. Any other questions? All right. So
Could
with
you
that, yes,
could you
another
re-explain
question.
why it's called a free moment, please?
Because that means regardless of where you put these two forces or the couple, wherever you put it on an object, the moment that they generate has nothing to do with where you have put them. Let me give you an example. Okay. This is a good example. So you want to loosen the bolts um, on the ring of your tire to, right? So regardless of where you put them, as long as, okay, the distance is the same and the magnitude is the same, doesn't matter where you put it. You can put it, if you have the possibility, you can put those in here and here, we'll do the same. So regardless of where you put these two on the object, put them here or here, do the same function, as long as the magnitude and the distance is the same, okay? And we'll do actually this fact, some problems to demonstrate that.
Wouldn't
In
those
fact,
that you just showed,
yes,
wouldn't those that like putting it in the other place, wouldn't that generate a moment in the opposite direction though?
no, in other words, let me draw my famous tire wrench, right? So this is force. I put them this way, right?
You had the
These
other
two.
ones like down though on your other diagram. The
Oh,
one,
was it the
yeah.
biggest one?
So as
Did
long
I
as
do
it's
it?
pointing in the same,
Oh, I see. I see. Yeah, right. No, I mean, same direction, same. Yeah, I should have put it
okay.
this going
So it
this
would
way.
generate a moment in the opposite direction.
Right, right.
Okay.
Yes, yes.
Okay. Thanks.
Sure. Good that you asked that question. All right. So we introduce, in fact, the concept of couple because that lays out the foundation for some really important things we'll do in rigid body equilibrium. It really lays out the foundation. And the concept that we are going to introduce, now that we have introduced the concept of the couples, is this. I'm going to discuss now a very important concept, which is called the concept of equivalent systems. And what is that? We want to demonstrate that this, let's say you have an object and you have a force acting on this object, F, at point A. How about if I consider another point on this object, point O, and then I draw or put two forces equal in magnitude and opposite direction at point O. I haven't changed anything on this object because these two simply cancel each other, don't they? Right? However, let's look at this, what I have done differently. If you look at this force and this force, right? They form a couple, right? So you can replace these two with the moment that these two represent, okay? And this is F times T. What that means is, this is a very important concept. If I have a force acting on an object, I can move this force to any point I want on the structure. In other words, I'm going to move this, put it here, as long as I would add at this point the moment that this force generates about that point. Okay? So, in other words, what this force does to this system, its action is the same as the action of this force and this moment. We call these equivalent systems. Let me, pose a simple problem. Let's say you have attached a cable to something, maybe a pole, that is exerting a force of 20 Newton. You don't like the location that this is attached. You want to simply move that to this location, any arbitrary location. You can, as long as you add a moment, which is the moment that this force generates about this new location. In other words, you can cut this out, put a rope here that exerts the same force, but you need also maybe a torsional spring of some sort that generates a moment, which is the moment of that force about that point. We call these equivalent systems, okay? And we will see the importance of this concept later on. You will see that if we have, for instance, a structure, later on we'll see that soon, next week, you have several forces acting on this structure. I want to replace all of them with a single force that acts only at this point A. What I do, add these up, put the resultant of all these forces here. However, if I want to move all of these forces here, I need to find the moment that each force generates about this point and add those up and put them here, okay? So in many design problems, this is what makes a big difference. Let's say you have a system supported by, a couple of brackets that are holding it. You don't like that. You want a single bracket in a different location. So you need to find the moments that those forces that those brackets represent generate about this new location, add up all those moments, and add up all the forces of those brackets and simply move them into that location. We'll see this concept very thoroughly later, but I just wanted to show you what is one of the most important reasons we study couples, because it is through couples that we could demonstrate the action is the same. So with that said, I'm going to do a few example problems here. Any questions so far? If not, let me do at least two problems. That's what I did in the other section. So let's say you have you have an object like this, maybe a pole or something. All these dimensions are given, 2 feet, 2 feet, okay? Okay. We have two sets of couples that are acting on this object. One of them is a 150-pound force acting at 30 degrees here, and another 150-pound force that is acting here. So these two form a couple. Another couple consists of this force of 200 pound, and the slope is given 3, 4, 5, and another force of 200 pound, which is also 3, 4, 5. Problem is asking us to find, the combined effect of these forces. Okay. What is the combined effect of these forces? These are couples, so they cannot move the object in any direction. So each of them represent a moment, which we call that a free moment. You can put it anywhere on the structure. So we need to find the moment of each force. Remember Mr. Saint Verignon? We introduced that beautiful concept that he discovered. We demonstrated that when it came to representing a force and its action for finding the moment of a force, we said that the moment of a force about a point is the sum of the moment of its component about that point. In fact, Saint Verignon's concept is more general than that. So in general term, we can express it this way. The action of a force on an object is the combined action of its components. So if we have a couple system here, let's apply the concept of Mr. Saint Verignon. What we're saying is these couple would do the same thing to this object as each individual component do. In other words, if this is a couple system, the components of these couples also form two couples. Look at the x component. This is 150 cosine 30, which is the square root 3 over 2. This is 150 sine 30, which is 75 pounds. So this is 75. This is 75, square root 3. The action of this couple is the same as the combined action of the couples that the components of this couple make. This is a one couple system, and this is another couple system. So if I want to find the moment that this 150-pound force generates, I need to find the moment that each of these two couple system generate. So what is the moment that this couple system generates? Would be 150 square root 3 times the vertical distance between them, which is given, is 4. But what direction they will act? See, they're like this. So rotation would be this way. So that would be negative. How about these two? They also generate a negative moment in this direction, and that would be negative 75 times the distance, vertical distance between these. Okay? So if you add these up, you see that moment of 150-pound force would be 819.6 pounds negative, or in the clockwise direction. How about this couple? You can replace that couple and into the action that that are represented by its components. In other words, if you resolve this into its components, okay, get rid of these. This is going to be, this one would be 3/5 of 200, so 120. This is 4/5 of 200, 160. So this is 120. This is 160 pound. So the moment of that 200 pound would be the moment of these two plus the moment that these two generate. So these two generate a moment that is counterclockwise. So it would be positive, and that would be 160 times the distance between the vertical distance, which is 2. How about these two? Also generate the moment that is counterclockwise, and the magnitude would be 120 times 2, and that adds up to 560 pound foot this way. So the total moment that these would generate would be the sum of these two, which comes out to be, if this is M1, this is M2, M1 plus M2 comes out to be 260 pound foot counterclockwise. Any questions? So,
Yeah,
yes,
question. For the first moment, would it be negative 150 root 3 over 2?
this one,
No, for the first one, for the 150 pounds.
right?
Yeah, would it be
Oh,
root
that's
3
right.
over
Sorry,
2?
it's 75. Yes, over 2. Yes, not 150 square root of 3 over 2. So it would be 75 the square root of 3. Yes, good observation. I did it right here. I forgot to convert that here. So thanks for the observation. Good point. Any other questions? If not, let me do yet another problem. Okay.
Sorry, one question. How do you know that it's going to be in the clockwise direction when one was in the clockwise and the other was in the counterclockwise for M1 and M2?
See, these two, let's look at these two. This one and this one, right? So this is like these, right? These two. So that means what? Is it clockwise or counterclockwise? They're rotating this clockwise. And how about these two? This one,
Oh, yeah, that one's clockwise as well.
right, these are also clockwise. So they add up. Whereas these two, this one is this way, the other one is this way. So it would be counterclockwise. And these two, right, these
Mhm.
two also would be counterclockwise. So
Mhm.
that's why these two are both positive and add up. Did I answer your question?
I was wondering why like the total, like when you add them up, is
Well, at
clockwise.
the end,
Yeah,
this
yeah.
is counterclockwise and this, yeah. Okay. Any other questions? So let me do another problem. Okay. All right. Okay. I'm going to do this problem. This is actually a problem from your book. I don't remember what problem it is, but it's a good problem. You have a beam or something pinned at this point A. The angle of orientation is 55 degrees. A couple is applied at point B and C. The orientation is given. These make an angle of 20 degrees with the line of horizon. The magnitude of these forces are given, 40 Newton, and the location of these are given. From A to B, the length is 0.39 meters. From B to C is 0.27 meters. So that's the problem statement or the information given. What we want to find is this, actually threefold. One, by using Saint Varignon's theorem, that is by resolving these couples into their components, find the moment generated by this couple system. This is part one of the problem. Problem also wants you to do this. Find the same moment by finding the vertical distance between them. In other words, instead of resolving this, can you find the vertical distance between these two with the given information and simply multiply the force by the vertical distance between them? Also, the problem wants you to try this out and demonstrate that since this is a free moment, if you take the moment of each force about point A and add them up, will this moment the same? Which the answer is yes, but problem wants you to prove that. Because as I said, these two forces don't do anything but rotation. So no matter how you find the moment that these two forces generate, the outcome should be the same. Whether you want to resolve them into their components or find the moment directly or find the moment of each individual about an arbitrary point and add them up, that's the same. In fact, the third part is something that we demonstrated in general, that if you have a force like this, if you take the moment about this arbitrary point, that is, find the moment, this moment, add them up, the outcome would be just that. But the problem wants you to prove that. So let's go one by one. First, let's resolve these two into their components. So you have this, which is 40 cosine of 20, this component, which is 40 cosine of 20, and then you have this vertical component, which would be 40 sine of 20 and 40 sine of 20. So in order to find the moment, in case 1, you simply write down moment of these two, or the couple moment generated by these two, which would be obviously clockwise, right? So it would be 40 cosine 20. But what is the vertical distance from here to here? In other words, what is this vertical distance? We can easily visualize that, okay? If you look at this triangle, okay, this angle is given, 55. So this distance, D, would be simply 0.27 sine of 55. So
Professor, could you
0.27.
move the paper, like move it
Oh,
down?
sorry about that. Yes, 0.27 sine of 55. In this triangle, this vertical distance, which is this side in this triangle, would be 0.27 times sine of 55. So that's what you write here. So with 0.27 sine 55. So this is the moment that this component generates. How about these two? These two would be this vertical distance, which is now 0.27 cosine of 55 times the magnitude of these two. And these two also generate a moment. These two generate a moment in this direction, right? So this would be negative, the moment of these two, clockwise. But these two generate a moment that would be positive, counterclockwise. So it would be adding 40 sine of 20 times 0.27 cosine of 55. And if you add these up, you get that moment would be 6.2 Newton meter clockwise. Any question? Now, the next part of the problem wants you to do this by finding the vertical distance between them. So the picture got a little bit messy. So let me redraw that in here. This is 55. This is that force at an angle of 20. This is the other one acting, this angle is 20. And, oh, this sun is really not helping. Okay, let me move it here a little bit. Okay. So how do I find this vertical distance between these two? This is what I should do. I have this distance, right? This angle is 55 degrees, right? All what I need is this distance, right? So what I need is this angle, which is, or maybe I should do that in a different color. This angle is 55. This is 20. So this angle would be 35 degrees. Can you see that? So this height, D, in this triangle would be 0.27 sine of 35. So I can directly find the moment, which would be 40 Newton times the vertical distance between these two, 0.27 sine of 35, if you could find that, you see that this comes out to be the same. Any question? Yeah, the sun is really not helping. Okay, so the third part is asking you to find the moment of each force, each of these, about point A, okay? Find the moment of each force about point A and add them up. In other words, what it is asking you is this, is this is that force, this is this force, find the moment of this force about A, find the moment of this force about A, add them up. Of course, the choices that you have, first you resolve these into their components and find the moment of each one of these forces about A, or try to simply find the vertical distance from A to this one, which you can, because you do have this angle again. This angle is that 35 degrees. So you can find this D1. And for this one would be this angle, this distance, which is D2. So, and that would be now this total times, in other words, this would be 0.39 sine of 35. This would be the total length times sine of 35. So you find these two, one moment in this direction, one moment in this direction, add them up, you should get the same result. I leave that to you to do it. Okay, any questions? So I will be sending you a whole bunch of things about the exam and all the information you need to know by email, including an old exam, a sample that would give you an idea what is kind of a typical type of questions that I may ask on this exam. Any questions by any chance? If not, have a great weekend, and I will see you on Tuesday. All right.
Yeah.
Thank you. And I'll be available at 11:30, my office hours.